there's a lot of different things that you're going to want to ultimately be modeling if you're trying to model a real world quantum network rolling here. Of course, all of the parameters in the memories that we talked about is going to be important. All of the parameters of the transducers, and these may be different between Alice and Bob, possibly. Of course, all of the fiber parameters and everything that I talked about there, as well as all the parameters that we have, of course, in the swapping station itself and between the beam splitter and the detectors. And also there's in general going to be some amount of loss when we're coupling these nodes and this and the station to this fiber. And beyond that, because we're using the Barret-Kok protocol here, we have to make sure that again there's timing and synchronization happening. So these components may also have clocks that have some uncertainty, and they're messaging each other to try to maintain synchronization. And you also have to specify sort of what the parameters are of the protocol that you're using. So, for example, how long does a node wait for a message before it just assumes that there was a failure that happened, for example, and starts again. And the general goal, right, should be to optimize over all of these to get the best average rate and fidelity of entanglement generation that you can. So I'm going to look particularly at the decoherence time here in this next little demo. So here I have the same thing as we have here, the Barret-Kok protocol, but I've wrapped it into sort of into several simulations where I apply a coherence time, a decay of coherence onto onto the memories themselves. So here I've said what we call idle noise models. So this will have a decay rate and a type of noise model, and this will describe how and how fast a given qubit will decay in memory, right? And so we can specify that within our memories, and then run several different simulations with different decay rates. So let's do that here. So we're going to run over decay rates in both Alice's and Bob's memories. It's going. It has a few simulations to run, so it takes a moment. I can show you, and it should be going. I can show you in the meantime what we're going to get. So funny, this is taking longer than I expected. Anyway, that will come up at some point. But what we should expect is this type of figure where you see here on these axes the coherence times of our two nodes, and so as we go to high coherence time, we find that we get perfect fidelity. Here we go. But for low coherence time, it drops off pretty rapidly to zero or close to zero, and this is because it takes a certain amount of time for the Barret-Kok protocol to actually succeed, right, and to do its thing, and there's time delays from transmitting messages. And so if your qubits in memory are waiting around and they wait too long, then they will start to lose coherence. And so that's what we're seeing here. And so given this setup, we can do this little experiment to see how our final fidelity would depend on the decoherence time.